A. Okay? Okay. Any questions so far?
Can you show the thickness again, please?
Because the Q, right, the thickness is 20 over here, right? So it's left and right. Because of shear flow, it goes left and right. That's why you have to consider the 2. 20 is because this at A, right, this thickness is what? 20. Sorry, one direction means one same direction. Okay, on the area of concern. Okay, so A is the area of concern. We are looking in the web region. Okay, Pei, does that make sense?
Yeah. So sir, so the point A is the intersection between the first rectangle and the two webs, right? So if we take the thickness is like 160 mm, would it be wrong?
Yeah, no point looking at the smaller value one. I just explained, right? You don't need to take the smaller. If you take 0.16, your answer will be different.
Yes. It would be different.
Why find the stresses? Why find the lower magnitude stress?
Yeah. Okay.
Right?
Makes
You
sense.
want to determine something that is a higher stress, but you also need to consider the right thickness. Right?
Yeah. Right. Right.
Okay.
Okay.
So the next one, okay, we are going to find. Okay, we want to find the shear stress at point B now. Right? So now we all know how to find. So this is 35. So we know that this is our centroid. So you want to find point B. How do you determine your first moment of area? Right? So your first moment of area, you have to consider left and right now. Okay? and you know why you attack from the bottom, right? Right? You apply the rules. Now your analysis direction changes. Right? Now your analysis direction changes already. Right? That's your analysis direction already. No doubt, V is coming from the top. Right? So we did an example just now. So it's why didn't we use, because if you use 0.16, the stresses will be lower, right? What's the point calculating a lower stress? Stavro, does that make sense? Okay, if I divide this by 0.16, the stresses will be lower. Yes or no? Yeah. Why are we calculating the stress that is lower? Okay, pointless. Okay. Now, then from here, okay, we are going to calculate stresses. Okay, we want to determine the shear XY at point.
Sir.
Yes.
Say on a test, like if you ask us, like first of all, would you ever ask us to find the I guess the lower shear stress?
Why would you want to find a lower value?
Just for testing purposes, because
no,
I'm just saying,
I don't ask stupid question like that, you cheeky sort. Oh, para.
Okay.
Okay. Okay. So we calculate for the weakest thickness. Jazia, this is just the beginning. Okay. Let's learn the fundamental first. Okay. It's not necessary calculate the weakest thickness. If now I want you to calculate at a point down here called alpha, what thickness will you use? You use 160, yes or no? Right? So don't get ahead. Later on, then we go into the aspect. Okay. Right. So now more important is the shear stress at XB. Okay. So as usual, we want to find the QZ at point B. Okay, so it's width times by depth multiplied by y bar. Okay, so you have to realize that you have left and right two. Okay, width is equal to 0.02. Depth is 0.03. Right? So now we have to find y bar. Okay, so the distance from here to here is 100 minus 35, which is equal to 65. Okay, so this is equal to 0.065 minus by 30, 0.03 divided by 2. Okay, so we calculate 0.065 minus by 0.03 divided by 2 times by 0.03 times by 0.02 times by 2 is equal to 60 times 10 to the power minus 6 meter cube. Let me do it again. 0.065 minus 0.03 divided by 2 times by 0.03 times by 0.02 times by 2 is equal to 60. Okay, we are good to go. So once you get your first moment of area, once you know how to find your maximum first moment of area, everything is easy. Okay, so shear xy at point B is equal to 90 times 10 to the power 3, right? Your Q is 60 times 10 to the power minus 6 divided by 5.813 times 10 to the power minus 6. Okay, and then twice for left and right, thickness is equal to 0.02. Okay, so the 2 down here is also for left and right. Areas, okay, web. The 2 down here is left and right web. Okay, so this is equal to 90 power 3 times by 60 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02 is equal to 23.224 times 10 to the power of 6 Pascal. I will do it again. 90 power 3 times 60 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02, 23.224. Okay. Okay. Now I'm going to do something else. Okay. I know this is the first time. Okay. We have a bit of time. I want to boost your confidence. Okay. I want to do some morale boosting for you guys. Now, what if now, okay, we want to find at the centroid, what is the stress? Okay, it's not part of the question, but let's do the part. Okay, so now I want to find the centroid. So we're going to do 2 approaches, and I want you to be comfortable. Either way, it works. It works. Okay, I want you to have the confidence. Okay, so we're going to do.
Sir,
Yes.
before you start the next part, can you just show the visual representation of the Y bar on the diagram, please? This part.
Y bar. On the second part, right?
Yes, please.
Okay.
It'll still be from the top,
Yeah.
the distance from the.
No, the distance will be from the centroid. The analysis is from the top. That's why you only consider this area down here. The analysis, sorry, the analysis is from Y max. Sorry, Y max. Nimata, does that make sense?
Yes, sir.
Okay. Okay. So now we want to find from the centroid. Okay, we want to find from centroid. So now we want to find the stresses at the centroid. Okay. So I will call this top section Below the centroid, I call bottom section. Okay. I want to do the easy one first. Okay. I want to do from the bottom section. Okay. So bottom section, from bottom section, we're going to find, okay, tau max. Right? That's our tau max. Okay. So we find our Q, Z, okay, and it's going to be at its maximum. Okay. So this will become width, depth, y bar. Okay. So now the width is 20 or 0.02. Or twice, because you got left and right. Okay. 0.02. The depth is 0.065. Okay, because the distance from here to here is 65. And now this is our y bar, because we are going to consider the whole area. Okay, so the y bar will be equal to 0.065 divided by 2. So this will be equal to 0.065 divided by 2 times by 0.065 times by 0.02 times by 2 is equal to 84.5 times 10 to the power minus 6 meter cube. Okay, so now we know that. Okay, so we just plug in the value, the shear max or shear XY centroid and we also know that this is also our shear XY max is equal to V 90 times 10 to the power 3. Area is 84.5 times 10 to the power minus 6 divided by 5.813 times 10 to the power minus 6 divided by twice and divide by 0.02. So this is equal to 90 power 3 times by 90 power 3 times by 84.5 times by minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02 is equal to 32.706 times 10 to the power 6 Pascal. Okay, that is your tau max. And if you look at here, it's higher than at point B and it's higher than at point A. Woo, lucky. Okay, now, okay, we are going to do from the top. Okay, from the top. Okay, from top section. Okay, so again, we are going to determine QZ max. Now, this one is a bit more different and it can be a bit more difficult. Okay, so for this case, you're going to find the Q of the flange plus by the Q of the web. Okay, so general formula is still the same. So Q, I'm just going to do the width, depth, y bar. Okay, so the width of the flange is 0.16. The depth is 0.02. And the y bar is what? It is it's equal to 0.035, right? Minus by 0.02 divided by 2. Okay. And then you have to find the web now plus. Okay. So we know that this distance from here to here is 15. Right? Because the entire thing is 35. Okay. So over here, the width is equal, so twice left and right. The width is 0.02. The depth is 0.015. Multiplied by the centroid divided by 2. Okay. So this is equal to 0.035 minus by 0.02 divided by 2 times by 0.02 times by 0.16 is equal to 80 times 10 to the power minus 6 plus by 0.015 divided by 2 times by 0.015 times by 0.02 times 2, 4.5 times 10 to the power minus 6. So this is equal to 84.5 times 10 to the power minus 6 meter cube. So what you realize is whether you take from the top or from the bottom at the centroid, the first moment of area is the same. And then you tell me, Eugene, can you plug in the formula on the top? So tau xy max is the same. Okay, tau xy max is equal to V is still the same, right? 84.5 is still the same, right? Divide by first moment of area still constant, the rule that we apply. At the centroid, you have left and right, so you divide by 2. And then the thickness is 0.02. Exactly the same. Is 32.7. Write this properly. It's 32.706 times 10 to the power 6 Pascal. Exactly the same. Okay. And I'm going to stop here for the lecture. Anyone? Any question?
Quick question. Are we expecting the questions all be these symmetrical problems, beams?
How do you mean?
Like the webs are the same thickness?
Yeah. I will not, if it's not, this rule will not apply, because if the web thickness are not the same, which you all will not learn down here, you will have a twisting effect, which you all will not learn. Okay.
Okay, thanks.
Anyone? That's a good question, by the way. Okay. If it's the web are in different size, yeah, this will not work at all. Where did you get 5.8? Where is 5.8? I'm trying to figure out where is the 5.8 that you told me that I get.
It's not in this page. It's IZZ when we found it before.
Oh, 5.813. Yeah, it's the IZZ. Yep. Thank you. Okay, so I don't see any question. I'm going to.
Sir.
Sir, yeah.
So, based on my understanding of this question, it requires the illustration to be done properly, because you break it down in so many